All right, everyone, here we go. Today we're starting with geometry. We're looking at angle and arc relationships, part 1. So when we classify the angle and arc relationship, what we're really paying attention to is the location of the center. So in my first two on this side, I'm really refreshing us of two angle relationships that we already know about. So the first type is when the vertex is the center of the circle. So here, vertex is the center. So in this instance, we often call that a central angle. So here's the center of my circle. Here is my angle, the rays of my angle. This right here is my central angle. And from here to here is its intercepted arc. So here, to remind you of this relationship, it's the most basic one that we have. This is the one that says that the angle measure will be equal to the measure of the intercepted arc. So right here, right, if that angle is 80, this arc measure would also be 80. If the arc here was, 47 degrees, the central angle would also be 47 degrees. Okay, our second relationship is when the vertex is on the circle. So you've heard us use that language before where we're talking about an inscribed angle. So the vertex is on the circle. So an example of an inscribed angle would be one like this. So notice where I'm putting the vertex right here. It's somewhere on the circle. This would be my inscribed angle, and this would be its intercepted arc from here to here. Another way that this could look, I could have a tangent line like so. Remember that a tangent line touches the circle in one position, so right here would be that point of tangency. And then I could have a secant line like so, and the secant line touches the circle, crosses with 2 points of intersection. So here's my tangent line, here is my secant line, and I could be looking at this angle right here. Again, vertex is on the circle, and its intercepted arc would be from here to here, for example. So here we know that our relationship is that the angle will have a measure that is half the measure of its intercepted arc. I could also say that the intercepted arc will be double the angle measure, 2 times the angle measure. So if this angle right here, let's say that the angle is 20 degrees, the arc here would be 40 degrees. If I made the arc here 100 degrees, the angle right here would be 50 degrees. So here are a few examples on these basic relationships. So here I'm saying, find the measure of each angle, arc, or variable in circle O. So if I call it circle O, then I'm calling it the center of the circle. Okay, if a line or segment passes through the center point O, then you can say that that is a diameter. All right, so first up, I'm looking at this picture. I have a circle. I also notice that I have these congruent chords here. I also notice that the triangle inscribed inside, I can see that it's isosceles. So a few places to build off of. First, I just want to be conscious of what I'm solving for. So I'm looking for P and A. So I'm looking for a major arc, and I'm looking for P and A, just like so. So that's ultimately what I'm trying to get to. So let's say that I start with this inscribed angle that's 40 degrees. Right, the vertex is right here on the circle. So I can double that angle to get to the arc measure, which would be 80 degrees right here. Okay, I also know, again, that these are congruent chords, and I know that arcs of congruent chords, they have to be congruent as well. So I know that all the way around my circle is 360 degrees. So if I take 360 and I subtract that 80 right here, I have 280 degrees that I have to split 2 ways, which gets me 140 degrees right here and right here. Another place I could have built upon as well is I could look back at the triangle, the isosceles triangle. So my vertex angle is 40, my 2 base angles would have to match also. So if I take my triangle, which is 180, take out the 40 degrees, I have 140 degrees left. split it two ways, these two base angles would both be 70 as well. And then if I doubled that 70, I could have gotten to the 140 just a different way. Okay, and now I'm asking again, I want PNA, so I need this whole span right here, that major arc. So if I add the 140 and the 80, I get 220 degrees. Okay, my next one here, I can see that I have all these congruent chords. You know, I love my words, so I've named it sparkled. So here I can see it's either a regular octagon inscribed inside of my circle, or I can picture those 8 congruent chords. And again, I know that arcs of congruent chords are going to also be congruent. So if I take that full 360 and I split it 8 ways, I can see that each of these arcs is going to be 45 degrees. So I'm going to mark that all the way around the circle. And then I'm going to go back and pay close attention to what I'm asked to solve for. I often fill out more information than I actually need. All right, so I'm asking for LA. So LA is a minor arc because I have that 2-letter notation. So I'm reading it from L to A, this span. Right, a minor arc should always be less than half the circle, so it should always be less than 180 degrees. So if I add up these 345s, I get to 135 degrees. Okay, let me slide up a little bit. Okay, the next example, nice throwback to quadrilaterals. So remember that if we have inscribed quadrilaterals, we know that the angles in the opposite position, they have to be supplementary. Let me remind you why. So if I look at this angle, this inscribed angle, vertex right here, this whole span from here to here would be its intercepted arc. And if I go over here, the angle opposite, right, here's the vertex on the circle, this whole span would be its intercepted arc. So I may not know exactly what the individual measures are, but I know how they're related. I know that each of these would be 1/2 of its intercepted arc. And since collectively their intercepted arc makes up the whole circle, I know that these two together have to be half of that 360. So these again have to be supplementary. When we have an inscribed quadrilateral, the angles in the opposite positions, they have to be supplementary. They add to 180. So right away I can get to x because I know that x plus 110 has to get me to 180. And then I can take away that 110 from each side, and I get that x is 70, right? 70 is the supplement of 110. So I get that x is 70. Okay, and then to get to y, right, I got to work for it a little bit harder. So to get to y, here I have to build up my equation. So I know that 3 times y plus 13 plus 2y plus 6 has to get me to 180. So here I distribute the 3y plus 39 plus 2y plus 6, all equal to 180. Combine those like terms, so the 3y and the 2y get me 5y. The 39 and the 6 get me to 45, all equal to 180. Take away the 45, so I have 5y equals 135. Divide each side by 5, and we get that y is 27. Okay, so if I plugged that back in, it would verify that these two angles in the opposite position have to sum to 180. They are supplementary. All right, next up. So here, we know that this is a diameter, right? We were told that from the beginning. So we were told that if a line or segment passes through the center, point O, right, there's our point O, then that's a diameter. So right away I know that I have a semicircle here, has to add to 180, and I have a semicircle here, has to add to 180 as well. Okay, we're also told that FOL, this angle, this central angle, and this one are in a ratio of 2, 3, 4. So I may not know exactly what their measures are right now, but I certainly know that they would reduce down to a 2 to 3 to 4 ratio. So I really just have to think, well, what is the multiplier that I could put on each of those to make it sum to 180, right? I know that all of these central angles, that's a straight pathway, they got to sum to 180. So I can go ahead and make x my multiplier. So 2x, here's 3x, here's 4x, and it has to sum to 180. So I can make my equation, 2x plus 3x plus 4x, all equal to 180. Combine the like terms, so I have 9x equal to 180. Divide the 9 away, and I get that x is equal to 20. Okay, great. So when I plug that 20 back in, I get that the central angle would be 40, and so would its intercepted arc. 3 times 20 gets me 60 right here. 4 times 20 gets me 80 right here. So what's important to note is that if I wrote the ratio as 40 to 60 to 80, and then I just divided away that 20, it would reduce down to a 2, 3, 4 ratio like we saw initially, just like that. All right, so now we're asked for the measure of arc FL. So right here, it's a minor arc, gotta be 40 degrees. And then we want angle measure ROU. So ROU right here, right, there's the arc that's 80. Its central angle would be 80 as well. All right, so this first page was meant to be a little review of relationships that we've already seen. So looking at what is the relationship between the angle and arc when the vertex is the center. So when the vertex is the center, we have a central angle. The angle is equal to the measure of its intercepted arc. And when the vertex is on the circle, the angle will be half of its intercepted arc. Or we can think of it as the intercepted arc will be double the angle measure. All right, I'm getting ready to flip. Okay, so give me 1 second just to get situated. So either flip or pull to your second sheet. Okay, and then here we're taking on 2 more relationships. So another option, which I alluded to in a previous video, was that, well, sometimes our vertex is inside of the circle. So vertex could be inside of the circle. What would that look like? Well, let's draw it. So let's say that I draw a secant line that looks like this, and another secant line that looks like this. And I put a little dot here for the vertex of the angle. So what matters is, well, what angle am I focusing on? I'm going to focus on this one. So if I'm looking at that one and I look at these 2 pathways that these lines make, I'm looking at the intercepted arc right here. And I'm also looking at the intercepted arc for the vertical angle to this one right here. Okay, and then the relationship that I showed you in the previous lecture was that the angle right here is always going to be the average of these 2 intercepted arcs. So I could also write that out as the angle is equal to 1/2 the sum of those 2 intercepted arcs. Okay, and then my last situation, well, if I run through my options, what have I seen so far? I've seen that the vertex is the center. I've seen the vertex is on the circle. I've seen the vertex is somewhere inside the circle. So what is our last option? Well, we know that that vertex could be outside of the circle as well. So vertex outside of the circle. So let me first draw you the different ways that that could look. So I could have a tangent line that looks like this, and then another tangent line that looks like this. Right, here's my vertex, it's outside of the circle. I could also have a tangent line that looks like this, right, 1 point of intersection right there, and then a secant line that looks like this. Here's that vertex, it's outside of the circle. Or my other way that I could make it look, right, I could have a secant line like so, and another secant line like so. And again, my vertex is outside of the circle. So here I have to focus on the two intercepted arcs. I will always have a bigger one. So here's the bigger one for all three variations. And I also have the smaller one. Let me mark that in green for these three variations. And I'm going to tell you the rule first, and then I'm going to explain it to you a little bit more. So here, my angle will always be 1/2 the difference between the two intercepted arcs. Okay, but I made you another little diagram just to help you see where that relationship comes from. So let me show you what I've come up with here for a moment. Okay, so here in my top picture, here I have two tangents, so like so, and I have the major arc marked at 200. So here I just want to think, well, what would be my minor arc right here? What would this one be? Well, I know that it's going to be a 360 take away 200. So I'm looking at 160 degrees right here. Okay, and I'm trying to figure out, well, what does this angle measure right here? I know that it should be 1/2 the difference between those two intercepted arcs. So I already have an idea that if I take 200 minus 160, I got 40, split that in half, that this should be 20 degrees. But I want to show you how we're getting there. So if I just mark this point of tangency here and the point of tangency here, and I connect right there, I'm really making a triangle. And I know that this angle right here will have to be 1/2 of 160, so got to be 80. And I know that this angle right here has to be 1/2 of its intercepted arc as well. It's the same intercepted arc, so it's got to be 80 degrees right here. So then I see, oh, I really have this isosceles triangle. My base angles match. Well, so do these segments right here. So we're going to see that when we have tangents to the same circle, we have a congruent relationship with those segments. We'll see that in a later video as well. Okay, so now if I focus on my triangle, if I have two angles that sum to 160, right, that missing angle, well, it has to be 20 degrees. Okay, so one fun thing to point out here also is that when we have the two tangents like this, so two tangents like this, if I know what this arc measure is, so see how here it's 160, I know that the angle will always be its supplement. So these two together must always sum to 180. So let's say that I made this where my finger is, let's say that I made that 100 degrees. My angle right here would have to be 80 degrees. These will always be supplements when I have these tangents here and here. Okay, but regardless, let's just check that formula. Is 20 equal to 1/2 the difference between 200 and 160? Right, 200 is equal to 1/2 of 40. Well, yes, absolutely. So I'm just checking that initial relationship where I told you that the angle will always be 1/2 the difference between those two intercepted arcs. That's when the vertex is outside of the circle. Okay, one other variation I wanted to show you is this guy right here. So as I've drawn it, I've drawn a secant and I've drawn a tangent. So here is my secant, right? It's slicing through the circle in two locations. And here's my tangent making contact in that one position right here. So here, what I'm going to do is I'm going to look at this point of tangency right here. And I'm going to connect it to this point right here. And I'm just making myself a little triangle to build off of. Okay, my starting point was that this is 100 degrees. So this minor arc is 100 degrees. So I know first off that this angle, so vertex is on the circle, this angle will be 1/2 of 100. So this angle, it's got to be 50. Okay, and then I see that together these form a linear pair, so they have to be supplementary. So right here, this angle has to be 130. All right, so far we should be okay. Okay, I can also fill in this arc from here to here. Let me block this out for a moment. So this is a diameter. So this has to be a semicircle. So a semicircle is exactly half the circle, so it has to be 180. So if this arc is 100, then this arc here has to be 80. Okay, and then if I build off of that 80, that arc being 80, this angle right here, vertex on the circle, has to be half of 80. So I get 40 degrees out here. Okay, and then the last thing that I want to fill in is this angle measure. So if I picture my triangle, so this triangle, I have this angle measure at 130. This one is 40. That's 170 degrees. So what's left over for it to be a triangle would be 10 degrees out here. So here, what I'm trying to follow to then use that formula, I'm looking at the two arcs here, and then the angle right there. So my angle should be 1/2 the difference between those two arcs. So let's just double check. Is 10 equal to half of 100 minus 80? And yes, absolutely, 10 is half of 20. So I'm just confirming that relationship. So again, when the vertex is outside of the circle, we know that the angle will be 1/2 the difference between the intercepted arcs. Okay, let me put that away and go back to my lecture. All right, so I'm just returning to example 2 right here for a moment. All right, so here I'm saying find the measure of each angle, arc, or variable in circle O. If a line or segment passes through the center point O, then consider it to be a diameter. Okay, so in the first one here, I see that my vertex is somewhere inside, but I can't solve for where X is right now. I can solve for this measure right here. Let's say that I call it Y. And I can do that because I know what Y's intercepted arcs would be. So I know that Y would have to be 1/2 the sum of 48 and 62. So Y would be half of 110, which would get me 55 degrees. But keep in mind, that's not what I'm asked for, right? This part right here would be 55 degrees. I want its linear pair, so I want the supplement of 55. So if I take 180 and I subtract 55, I get 125 degrees for X. Okay, in my next one here, I see that my vertex is outside of the circle. So I know that X is going to be 1/2 the difference between these two intercepted arcs. When they're two tangent lines, it's really splitting it into a major arc and a minor arc. So if this is 240, I need to do 360 minus 240 first, which gets me 120 right here for my smaller arc, minor arc. So now I can say that X will be 1/2 the difference between the two. So half of 240 minus 120. So half of 120 will get me 60 degrees. And I just want to remind you of something else. Remember what we showed earlier, right? If I connect from here to here, only when it's the two tangents like so, I'm getting this acute triangle that looks like this, where these two base angles got to be 60 and 60, which means that this angle measure right here is going to end up being the supplement of 120. So I got a 60 right here, right? This would be a nice equilateral triangle. I just didn't know that from the very beginning. Okay, so only when we have the two tangents, so tangent means touches the circle one location, then I do know that this angle measure will be the supplement of this intercepted arc right here, only for this variation. All right, next up, C. So here again, I see a vertex inside of the circle, and I can see that my angle measure is 84. One arc is 100. I need to know what this one is. So if you'd like to follow a formula, we know that the angle measure, 84, is going to be 1/2 the sum of X plus 100. So I have my equation. You know I love to clear a fraction, so I'm going to multiply each side by 2 first. So I get 168 is equal to X plus 100. Okay, take away the 100, and we get that x is 68. So 68 degrees. Okay, one other thing that I can note is that 84 is an average of two numbers. So if 84 is an average of two numbers, numerically it's going to be equidistant from 100 as well as whatever x is. So 84 plus 16 is going to get me 100. So 84 minus 16 will get me x. So I can get to the 68 just a different way, right? When a number is an average, right, it's equidistant to the two numbers that cushion it. So I can see again that 84 plus 16 would get me to 100, and 84 minus 16 would get me to my 68. Okay, next up here I see that my vertex is outside of the circle. So that angle of 37 is going to be equal to 1/2 the difference between the two intercepted arcs. So here is my structure. Again, you know I love to clear a fraction, so I'm going to multiply each side by 2. So I get 74 is equal to 136 minus x. I'm going to go ahead and subtract that 136 from each side. So negative 62 equals a negative x. Divide each side by a negative 1, and we get that x is 62. So my missing smaller arc is 62 degrees. Okay, next up here. Here I see vertex is outside of the circle. I'm given the angle measure at 92, and here I want that major arc. So here what I really need to remember is when I have the two tangents, I know that this smaller arc here and this angle right here, they're going to be supplementary. Why is that? Because here I could connect those 2 points of tangency here, okay? And then no matter what, remember that these two angles are going to be congruent. So I've made my triangle. I know that 92 degrees is already occupied. That's my vertex angle. I'm left with 88 degrees, which would split two ways, making this angle here 44 and 44 degrees. So that arc that I wanted, right, that is 88. So again, in this variation and only this variation, when we have the two tangents vertex outside, the angle here is going to be supplementary with the arc right here. So that arc is 88. So now to get to what I wanted, to get to the x, I need to do 360 minus 88, and I get 272 degrees, of course. Okay, one last variation. So here I'm asked to solve for x. Okay, and when I look at my picture, I can see that, well, I have the angle, the vertex is outside. I have the larger of the two arcs. I don't know the smaller one, but I have an idea of how to get there. Okay, and then ultimately I want this guy right here. So what I'm going to do first is I'm going to solve for what I can solve for, this part. I'm just going to call it y for a moment. So if I call that y for a moment, let's solve for y. So I know that the angle 74 is going to be equal to 1/2 the difference between 190 and y. So now I'm going to solve for y. So I need to clear my fraction, multiply each side by 2. So I have 148 is equal to 190 minus y. Take away that 190 from each side. Negative 42 is equal to a negative y. Divide that negative 1 away. So y equals 42. Remember what I said, that's not what I'm solving for. I'm going to need it to get to x. It's that initial hurdle that I had to cross. All right, so now that I'm there, remember that arcs of congruent chords are always congruent. So I may not know what these individual measures are yet, but I know that they're going to be the same. They have to be the same. I know that these chords cut off the same portion of the circle. So these two arcs have to match. So right now I know what these two measures add up to. Right? I can add 42 and 190 and see that I have 232 degrees already used. So what I would need to do then is take my 360, subtract that 232, And that leaves me with 128 degrees left, right? I got 128 degrees here and here. So I need to split it 2 ways, which is going to get me 64 degrees for each of these 2 smaller parts. So x ends up being 64 degrees. Right here would be 64 degrees, and so would this part right here. All right, that's my lecture for today. I hope everything made sense. Have a wonderful rest of your day.